Okay, Assalamualaikum and good day everyone. So today is about discrete versus continuous change in topic 1. Okay, we have learned earlier about difference equation compared to differential equation. So now it's about discrete versus continuous change. So some changes take place in discrete time intervals such as depositing of interest in an account. So normally the compounded amount of money has been calculated in interval time. For example, quarterly, um, yearly and so on. So that is about discrete time interval. So the process is called, or the model that we develop is called difference equation. Okay, but some changes happen continuously, such as change in the temperature of a cold can. Temperature, normally we measure the change continuously. For example, in 1 hour, what would be the change in temperature? Or in 5 hours, or in 10 hours and so on. So we measure the change continuously within the time duration given. So that the study that we measure or the observation that we do in the time frame, for example 5 hours, 6 hours and so on. So that process occur continuously. So those process model involved is called differential equation. Okay, now look at this example, growth of a yeast culture. So growth of a yeast culture normally is a continuous process because it is measured continuously on an interval of time given. Okay, so now let's see an experiment measuring the growth of a yeast culture, which is data collected or the observation obtained is given by the following table. Okay, let's say the observation we do is note on this following table, where n is the number of time in hour. For example, start with 0. The yeast biomass is given by P sub n. Initial biomass of the yeast is given by 9.6. It's measured in maybe in gram or milligrams. Depends on the unit that we use. And then in 1 hour, it is the growth become 18.3 gram, and the change here would be 8.7 is the difference between 18.3 and 9.6. Okay, and then the next hour, 2 hours, the growth measured is 29, and the change is 29 minus 18.3 given by 10.7. Okay, in 3 hours, the growth become 47.2, and the change is to 47.2 minus 29 is 18.2. So this is how we measure and note the data in the form of table given here. Okay, and here we model change given by delta P sub n is given by this one that we have learned earlier, given by the biomass of yeast at time n plus 1 minus biomass at time n. Okay, so now if we look at the change in the biomass, which is given by ratio delta Pn over Pn, it is roughly a constant. This one is normally we do it by try and error, by finding the estimated constant. So in this process, it is given that the constant is given by delta Pn over Pn. Delta Pn over Pn here. So every delta Pn over Pn, the value is about this value. But for this case, it is not the exact value. We take the average. average of delta Pn over Pn. So take the value of delta Pn over Pn here, and then get the average, a total of delta Pn over Pn divide by what? 1, 2, 3, 4, 7. Okay, divide by 7, so the value becomes 0.6057. Alright, so now I try to calculate it and try to get this value. Okay, now from this ratio equation, we have delta Pn. Bring Pn to the right side, it becomes the constant 0.6057 Pn. So this is the change model, which is so when we rearrange in the form of P sub n plus 1, it becomes 1.6057 Pn. Okay, since delta Pn is Pn plus 1 minus Pn, so we rearrange the equations, it becomes this one. Okay, try to do it as we construct it in the earlier example. So we should be able to get this equation. Since the ratio given by this Pn plus 1 over Pn become 1.6057, so this value is greater than 1. So from the ratio, if the value is greater than 1, so we can predict that the model or the population will increase forever because it's greater than 1. The value of Pn plus 1 is always greater than Pn. So we can predict in the long time, the biomass will become bigger and bigger. It will grow without bound. Okay, in example 1.2.2, so under the restriction, suppose that we have a table given in the textbook. The one I will show in the textbook, but I do not have it here. But I can show you that in the textbook that we have a plot of yeast biomass growth. It is given by this model where the value is close to a constant value, which is given by 665. Okay, so we have this kind of sequence, and we can see that in the long run, the growth of the yeast will become constant at limiting value 665. Okay, so now the graph of the population appears to be approaching a limiting. Okay, we may propose that delta Pn change in the yeast biomass is proportionate to value 665, meaning that the limiting value minus Pn times Pn. This is proportionate to this equation. Okay, this one is done by try and error to see what is the constant given a limiting value. Alright, but for this case, after an experiment or after the try and error to find the constant is given by this relationship. Okay, so by computing the ratio, so now we take the ratio delta Pn over the right side value, the ratio between left side over right side value, we can estimate or we can calculate the constant given by this equation, by this number. Okay, so you can try to calculate this and try to find this value, then only you can understand. Okay, that value, the 0.0 something, the one that small number, is actually the average. Okay, it takes the average to find, because the number we don't get the exact constant, so we go for the average of the ratio. So every delta pi over 665 minus pi times pi from data 18 data altogether implies that, So this constant, this is the proportion constant or the ratio constant that we calculate earlier. So we have the equation delta Pn equal constant time limiting value minus Pn time Pn. So rearrange the equation in the form of equation Pn plus 1. So we have this equation. Given initial value of the yeast is 9.6. Okay, so this is the model. Okay, actually this is the model, and we are going to use this model to predict values at any given point. Okay, any given n. So we are going to use this one. Okay, actually given the ratio between Pn plus 1 minus Pn versus right side 665 minus Pn time Pn, we will be able to get a straight line because the ratio between the right side and the left side is given by a constant. So it means that from a curve function, we transform it into a straight line. Okay, this is to find, actually this is the conversion from a curve function to a straight line is actually to see what are the constant that relate, okay, the constant that relate the two equation, the two variables. Okay, this is about conversion or transformation from a curve function into a straight line so that we can see the constant change in the growth of the biomass. Okay, so now, so since we are able to construct the model for the growth of the biomass, we need to compare. This is the validation part or the verification part where we need to compare actual and the model. Okay, so here we have, okay, this one not in the color mode, but actually if it is in color mode, we have actual data. The actual data is the one. Actual data is the one that we plot earlier. This actual data, and the other data given by another color, let's say blue, is the one that we construct one by one, starting from P0, 9.6, and then from this one, the constant is given, find P1, P2, P3, and then we plot that one. P0, P1, P0 is at the same point, because we start at 9.6. And then P1, P2, P3 for the model that we construct would be given different data. So this is the comparison, the actual data and then the model data, the experiment. Okay, the actual data is called the actual data is experiment data, and the model data is called the predicted data. Okay, experiment data or observation data and the predicted data. So it's about the same. So we can, if the error is very small, so we can use the model to predict what is the value of the gross biomass when time is given at it's given specifically. For example, 15, from our observation, the time n is actually 15. So next we want to find what is the, when n is 16 hours, 17 hours, and so on. So we're going to use the model, okay, or the equation that we construct in the difference equation.